Hello and welcome to this video about skin depth. Skin depth is a measure of the amount that an electromagnetic wave can penetrate into a good conductor. Just by looking at this diagram, you can see that the wave starts to attenuate or decay as it passes into the good conducting material. It has an exponential decay as a function of the distance into the material that it penetrates. So its intensity decreases exponentially. Its wavelength decreases too. Skin depth is defined to be the distance penetrated into the material, so that its amplitude decreases by e to the power of -1 or 0.368. This is the amount of distance that the wave is attenuated by 1 NEPA. The amount of distance that attenuates it by a half or a tenth can be derived from this skin depth distance. Here is a list of all the quantities that we'll be working with. Most of these will be familiar to you even if you only gained a high school knowledge of physics. I've circled 4 of them in red. The permeability is an amount of a magnetic property of a material and is usually almost always equal to the permeability of free space, which is a constant. The conductivity is the amount that a material can conduct electricity. The permittivity is the amount that a material is a dielectric and won't be used in any of the equations that we derive. The current density is the current per cross-sectional area that passes through a conductor. So now to derive the skin depth equation. I'll just try to quickly summarize the plan in doing it, so as to make it all easier to follow later on. We'll be using lots of different sorts of math, like vector calculus and solving differential equations. We'll firstly start off with Maxwell's equations and modifying them for use in a conductor. We'll then manipulate these equations using vector calculus so as to find this differential equation here, which describes electromagnetic wave propagation in a conductor. We'll then solve this equation using this form of solution given here. We'll substitute it back into equation 10, so as to eventually get this equation which we need to solve for K. K will be complex, so we'll need to find both its real and imaginary parts. The real part, alpha, will be our attenuation. So this will be our first value for alpha, which looks fairly messy. Fortunately, we'll be able to simplify it using some almost equality mathematics, which is done a lot in physics. We'll then find the value for the skin depth from this value of alpha. So now we'll start with Maxwell's equations, given here in the form with only E's and B's and no D's or H's. We know that we'll be using them inside a good conductor, so this equation will be used. And there won't be any residual charges about, so charge density is set to 0 everywhere. So these are the 2 Maxwell's equations that will remain unchanged. And when we substitute 6 into 1, we'll get this equation 7. That says that there is 0 electric charge nearby. And substituting 5 into 4 gives us this equation number 8, and which looks complicated. So this is the equation that we'll be working on. And now to use these Maxwell's equations inside a conductor to find the differential equation that we need to solve. We'll take the curl of both sides of equation 3 to get this equation 9. We'll evaluate the left-hand side of this equation first. This is what taking the curl of a function twice looks like. And so from equation 7 we know that the divergence of E is 0. So we're left with the Laplacian of E. So now we'll work on the right-hand side of the equation. We can take the derivative function outside of the curl function as though it is a constant. We can then make this substitution in this equation, and so we can get the time derivative of this expression. And so putting these two sides of the equation back together gives us this equation, and we can manipulate it so that the right-hand side is 0. And so now we have to solve this differential equation. We can simplify it to this because it is only propagating in the x direction, and we can ignore the y and z directions. This is the general solution for this differential equation. It is expressed as a complex number function. So we'll calculate each of the terms of equation 11. Since this term is an exponential equation, the function gets multiplied by k twice in this case, and it may be simplified to be this equation. Similarly, this equation gets multiplied by I omega in this case, and this is what this term is equal to. And so we can substitute all of these terms back into equation 11 to get this equation. The function E can be factored out, and since it is non-zero, we only need to solve this expression for k, and we'll tidy up this expression so that everything is positive, and we can deduce from this expression that k is complex, and so we have to find both of its complex components. So now we'll start with these two equations so as to solve for k. We only need to find k so as to find the equation that describes the electromagnetic wave propagation in the conductor. We'll substitute this expression for k into this equation, so now we need to solve for both alpha and beta. Expanding out this expression gives us this. We may separate out the imaginary and real parts of this equation to give us these two equations. And we can tidy them up so as to put the variables we're trying to find on the left-hand side and the variables we already know on the right-hand side. I've decided to show you how to do it so as to complete the derivation. It is important to see how it's done. We square both of these equations so that we can more easily separate out alpha squared and beta squared. We are in a good position to get alpha squared plus beta squared from these two equations 21 and 22. So starting with these two equations, we'll get alpha and beta. Adding these two equations together and simplifying them gives us this equation. And square rooting both sides gives us alpha squared plus beta squared. If we add these two expressions like this, we can get alpha squared. And we can get alpha by square rooting it. Alpha can be either the positive or negative of this expression. We'll keep this in mind since it needs to be negative to make the wave attenuate. We may follow a similar procedure to find beta. This expression for alpha looks nasty, but there are ways of dramatically simplifying it. We slowly move the variables around so as to get numbers like 1 inside the expression. And so we get this expression for alpha, which even though it looks as messy as before, is able to be simplified using some clever approximations. We similarly get this expression for beta, and so starting with this expression, we try to get a simpler formula for alpha. This expression is true for all good conductors. It means that this expression is much larger than 1 to the point where we can ignore 1 if we have to add it onto it. And so we can write this approximation and use it to simplify equation 29. And we can even expand this approximation to include this next approximation. And so we can substitute this approximation into equation 29, the equation we're trying to simplify, to give us this equation. And so finally we end up with this much simpler formula for alpha. We can similarly find the simpler formula for beta, so beta and alpha are equal. And so we can use this value of alpha to find the skin depth delta. We use this expression because we're trying to find the value for x so that the magnitude of the wave envelope is e to the power of -1. We'll set delta to be this value of x, and we'll substitute it in for x. We'll ignore this term because we're looking at the exponentially decaying envelope and not at the wave itself. And we'll ignore this term because we're not looking at its behavior in time. We're taking a small snapshot during an infinitesimally small time interval. And we can eliminate the values of e straight away and reduce this equation to being this. And we can take the logarithms of both sides. And we can get the skin depth delta. We can use this equation to get the skin depth in terms of the proper wave frequency f. And substituting this equation into the other one gives us this. And so we end up with this equation for skin depth. It is also a good idea to see the relationship of the electric field to the magnetic field. The magnetic field B has a similar equation to E. Using these equations, we get this relationship for the B and E fields. Evaluating this equation gives us this to start with. We then get this solution to the differential equation. This is how E and B relate to each other. So this is the ratio of E to B. So we know that K is complex. And since alpha and beta are equal, then 1 plus I is a factor of K. So this is the ratio of the electric to the magnetic field. And so it simplifies to be this, although I left the number 1 minus I factored. And because of the 1 minus I term, then E and B are out of phase by pi on 4 or 45 degrees. So in order to see exactly if B lags E, we'll set the real value of the complex number to be the coefficient of the cosine component of the wave, and the imaginary part to be the negative sign component of it. We set it to be minus sign because the coefficient of t is negative omega. So we'll set B to be purely real, so it is equal to its real component, and thus equal to only the cosine part of this wave. Then we'll calculate E in terms of this value of B, which is given by this formula that we've found earlier. And we'll perform this very small substitution here so as to emphasize that B is purely real. So we can substitute these cosine and sine values in for the real and imaginary parts of the wave, which gives us this waveform for E. So we can say that E leads B, or B lags E, by 45 degrees. And so we can have a look at these waveforms here, and in terms of x, E does lead B. And we can see the relationship of B to E, and how they don't exactly match up like they do in free space. But B lags E. we'll take coming out of the page to be positive for B. Now we can get this ratio of the amplitudes of the electric field to the magnetic field in terms of omega, sigma, and mu. And after this substitution, we get this quantity. And slowly manipulating it, we get this real quantity multiplied by this simple complex number. We can manipulate it further so that the magnitude of the complex number is equal to 1. So we can easily find the ratio of the amplitude of the electric field to the magnetic field. Since the two fields aren't in phase, this can be thought of as the ratio of the exponential envelopes of these two amplitudes. We can then find this ratio in terms of the proper frequency rather than the radial frequency. And now to find the wavelength and velocity of this wave travelling in this good conductor. We'll start with the wave number equation as given here, and we'll substitute beta in for k, since beta is the oscillating part of the wave number for this propagating electromagnetic wave, and thus we can find the wavelength lambda in terms of beta. And we can make more substitutions and find the wavelength in terms of the skin depth. And we can find the velocity of this wave by starting with this velocity equation. And making some substitutions, we can find the velocity in terms of the skin depth and frequency. We can then get this equation. And so using this skin depth equation, we can manipulate it to find this velocity equation. And this is the velocity in terms of the variables that have been given to us and did not need to derive. And now to find the value of the wavelength of this electromagnetic wave in the good conductor using the variables that we've been given, like frequency, permeability, and conductivity. We'll start off with these two equations. And after making this substitution, we get this new expression, which simplifies to be this equation, which we can use to find the wavelengths of electromagnetic waves in a good conductor. And now to calculate the depth into a good conductor that an electromagnetic wave has to penetrate so as to be attenuated by an amount n, where n can be a half or a third or any number smaller than 1. Here in this picture you can see this penetration depth being denoted by delta subscript n. If the skin depth has been calculated, then this other penetration depth can be calculated from it. So we'll use these two expressions. The first one is a definition of this penetration depth to attenuate it by n. The minus sign was included just like it was for the calculation of skin depth when alpha was derived. Negative alpha was also a solution. And substituting one equation into another gives us this equation. And taking the logs of both sides gives us this. And rearranging this equation gives us this equation that we can use to find this penetration depth from the skin depth. And now to use these equations to solve some sample exam problems. Here we're asked to find the skin depth of an electromagnetic wave in iron. So we're given the frequency, and I like to write it out in JavaScript scientific notation. We can use the permeability of free space because the material can't respond quickly enough to such a high frequency, and we can look up the conductivity of iron in a table. We can then use this formula that we've derived and plug all of the numbers into it. And so we end up with this skin depth for a wave in this material, which is very short. And now for this second example, we're given the skin depth, but have to find the frequency of this wave in the conductor. We plug in the numbers similarly like we have before, using the permeability of free space and the conductance of the material we've looked up in a table. However, we write in the skin depth instead of the frequency this time. We start off with this skin depth equation that we've just recently derived. We manipulate it to make the frequency into the subject of it. We plug all of the numbers into it, and then we get this answer for the frequency. And now to get the velocity of this wave and the ratio of electric to magnetic fields of this same wave. We'll start with finding the velocity. We'll use the permeability of free space because the frequency is too high for the material to respond. We'll look up the conductivity of this material from a table, and we've been given the frequency, and we'll write it out again in algebraic form. And we'll use this equation that we've derived earlier, and we'll plug all of the values into it, and then solve it. The wave moves a lot slower in a metal than it does in free space, by a factor of 10,000. And now to find the ratio of electric field to magnetic field of this wave in this conductor. Since these fields are not in phase, then we'll calculate the ratio of the magnitude of their exponentially decaying envelopes rather than their actual values. So this is the equation that we'll be using. And so we'll plug all the numbers into it. And so we get this value, which has the same dimensions as a velocity. And now for this problem, we must find the wavelength of an electromagnetic wave in a slab of aluminium. We can set these variables. The permeability is set to equal the permeability of free space, and the conductivity of aluminium can be looked up in a table, and we're given the frequency of this wave. We use this equation that we've derived earlier to find the wavelength from these variables, and we substitute all of the numbers in, and so we get this solution. And now in this question, we've only been given the skin depth and don't know the type of metal or frequency of the electromagnetic wave, and we have to find the depth of penetration to attenuate it by 0.2 or a fifth. We'll just write out the known quantities here. These are the only ones we'll need, and we'll use this equation here that we've derived earlier, and we'll substitute all of the values in, and then when we evaluate the logarithm we get a negative number because 0.2 is less than 1. This is cancelled out by the other negative sign in front of the function, and so we get this answer, which is fairly close to the skin depth. So I hope this video has been helpful for you in your quest to study skin depth and the propagation of electromagnetic waves in a metal, and I wish you all the best in your quest to understand it.